In this experiment, we're going to look at the properties of gases. And we'll do that with some very simple apparatus. We just have a balance here and a used can of coffee that will fill with different gases and then actually measure the mass of that gas in that container. So the first thing we'll do is balance this container, which currently just has air in it. It had been opened and then closed again. You can see the balance reads very close to 0. We've removed the pan from the balance so that it comes out roughly balanced when we add this coffee can to it. The small gram scale, which is on the front side of the balance, as you can see here, reads 4.5 grams at the present time. And that's the one that we'll have to trim when we change what is inside that container. So I'm going to go over, take that container off, go to the other room where we have a tank of helium. I'm going to fill that container with helium gas and then bring it back, and we're going to measure its mass. So the first thing I'll do is take it off, and I will be back in a moment. So now I'm back with a container. I put some helium inside it. It's pretty easy to do because this seals, and you open this up and flow helium up in here. It rises up and fills the container until it flows out. You snap that back on there, which I'll show you. I'll go back over and we'll take the camera over there later. So to get this to fit, I have to turn this outside. So it goes this way. And we'll stick it on there. And you notice that it's not balanced anymore. It's a little too heavy. So we're at 4.5, and I'm just going to move this back until it balances. Looks like it's about 2.1 right now. So just to show you what happens, I'll take this off and I'll turn this upside down. I should feel a flow of helium when I open it up, and I do. I should breathe that. So you can actually hear it, and then I'll do this. I'll put this back on here. Now that's got nitrogen in it, mostly air, and it's too heavy. About the same amount, you can see it. So we'll go back over here. Should come down about 4.5, which is where we started. Looks like it's pretty consistent at 4.6. So that's air. We put helium in, and it had less mass in it. The lift, when you think of helium as lifting something because of the displaced air, in the ideas of Archimedes, it works. That's why balloons lift. In this case, the volume is the same. So although I replaced what was inside with air, the lift which was provided, just the displaced volume of the air surrounding this, is the same in both cases. So the two different measurements is actually the difference in the mass of the air that's in there now and the helium that was in there when we did this experiment. So just so that you'll see that this is repeatable, I've filled the container again with helium. I'm going to put it back on here. You can see it's lighter now than it was, and I'll go back over here to the setting we found before, about 2.1 or so. A little heavier this time. So it comes out about 2 point, maybe 4 this time. Pretty close to the same. So now just to demonstrate, I hope this will work, I'm going to take this top off and take a deep breath of this. It's supposed to be helium, remember? So it's going to rise up. It'll stay inside the container but until it turns upside down. Now, see, that's what happens. Helium gas changes the speed of sound, and just a little breath of it, and we got to change the frequency. So helium and air have different masses. So now it's all the same, except this time I put nitrogen in here. So instead of air, it's N2. And let's see what we have. Put that on here. What do we have here? Look over here. What do we have for N2? Not 4.5 anymore. About 4.4 maybe. Close to that of air, which it should be because air is mostly nitrogen. A little bit less. So I just wanted to show you how we fill the container with helium because it's an interesting trick and it actually makes the experiment work easily. So this is just a standard discarded coffee can. It's got a seal on the inside, and when you put this top on there and snap it in place, it will hold the gas inside for quite a while. So all I really have to do is get gas in there and get the top on it, and you can actually do that with a flow of gas from a compressed gas cylinder. This is helium, laboratory grade at high pressure. When I open this valve, it comes up and tells me I've got 8,000 kilopascals of pressure inside this tank. I have a regulator which reduces the pressure so that over here on the output side it's about 1,000 kilopascals. And then when I open this small valve, the gas will flow out through this hose, which is normally connected to an instrument in the lab, but I've just borrowed it for this. So when I open that up, you can hear the helium. And then we'll just put it up inside here like that. And a little lock, I can probably get it to work here. So we'll just open this up. It's filling that can up. And just kind of pull it over like that. Try to hold it level. And just fill it up with helium. Snaps that. So now I've got a can of helium, and that's what we measured when we weighed the helium gas inside the can. So to measure the volume of the container so that we'll know how much gas we had when we weighed it, I've got a beaker here that's graduated pretty accurately, and I filled it to the 1 liter mark, the 1,000 milliliter mark, 1,000 cubic centimeters at this point. I'm just going to pour that in here. Comes up about halfway, so I'll go get some more water and we'll do it again. And we're ready to do the second liter here. Pour that in. Pretty sure it won't overflow. Not quite at the top, so we'll need some more. Now the beaker is conveniently graduated. It's full at 1,000 milliliters, but it also tells me how much I've taken out as the level goes down. So we'll just add until it tops off at the top of this. Try not to overflow. Make a mess here. That's pretty close. You can see we're down at just a shade more than 300 milliliters additional to the 2 liters that was already in there. Now we have a top, and the top goes on there like that, and it seals on that inner edge. So I'd actually like to add some more water to measure the volume inside here, and try to do that without, it's not quite level here, but we'll get it pretty close. So allowing For the top, we're now down 400. So we've got 2.4 liters of volume in this container that contained the helium and the nitrogen that we measured on the balance. We're going to do an experiment today to look at how the pressure changes in an enclosed volume when we decrease the size of that volume while keeping the number of atoms or molecules in the volume constant. So this demonstration apparatus will let us measure that to enough precision to be able to show that it holds up as one of the fundamental ideal gas laws. So we're looking at a gauge which measures pressure. It's a mechanical gauge. It actually reads pressure by force. And there's a spring here. This C-shaped object is a spring which will move in response to pressure, and then it's amplified by a little gearing mechanism so that that needle is calibrated to read in pounds per square inch. This chamber is open right now to the atmosphere at this side. And then I have a standard little syringe up here, which is calibrated in cubic centimeters. So that's 5, 10, 15, 20, 25, 30, and now all the way out at 35 cubic centimeters in the volume here. And we're going to change the volume of that by depressing this plunger while we look at how that pressure changes. The current pressure is atmospheric pressure, which reads on the gauge right there at about 15 pounds per square inch. And we can actually measure the temperature. You may be able to see this with this infrared thermometer that looks at the black body radiation from the plastic that's holding that chamber, the gas in that chamber enclosed. So it reads about 74 Fahrenheit at this point. That temperature will stay about the same as we do this because this whole apparatus is in equilibrium with the room. Now we'll start with atmospheric pressure. This is open. The gauge is attached to that fitting through a small volume mechanism which actuates the spring that measures the pressure inside that chamber. So I'm just going to connect this to that by depressing this fitting. Sticking this little thing in there like that. It should there. So now we're measuring the pressure that's over here in this volume. And I'm just going to decrease that volume. We start with 35. And that's 30. And then 25. And 20. And 15. And one more step. I'm going to go down here to 10 cubic centimeters. And then gradually open it up to 15, 20, 25, and 30. Letting the force of the gas actually push it out to 30 here. In this part of the gas law experiments, we're going to look at how reducing the temperature of a closed volume of gas alters the pressure in the gas. And just once again, we have a sphere. It's 10 centimeters in diameter, connected by a hose to a pressure gauge, which measures the pressure inside the sphere. We have previously had the sphere disconnected from the gauge so that the whole system was at atmospheric pressure. And the pressure that you're seeing on the gauge there now, which is about 15 pounds per square inch, should be the Earth's atmospheric pressure in this room today. So I can just tap on the gauge a little bit. Sometimes it gets stuck, but just make sure it's in the right spot. And then I'm going to measure the temperature with the thermocouple, and I have a little thermocouple gauge here, which you can read. Currently reads 21.5, and that's the temperature at the end of this wire pair, where two little wires are welded together to make a joint that has a voltage that's proportional to the temperature, and then that's interpreted by this little meter here in degrees Celsius. So that temperature, 21.8, as it reads right at the moment, is representative of the room temperature. And then in the container here, the cooler, I've got a chunk of dry ice. So down inside here, dry ice bag right out of the grocery store. And I've crushed it up a little bit so that the dry ice itself is in small pieces, so that when I put this sphere down in here, I can get the sphere pretty much surrounded by a dry ice. And we're going to do that. We're going to see how the temperature changes. It will take a while for the sphere to come to equilibration with the dry ice, so I'm going to stick it down in there pretty good. We'll cover the whole thing, and then we'll wait. We'll come back in a while after that's had a chance to really cool down well, and see what pressure we have, and also see what temperature the sphere is at. We've had a few minutes for the sphere and the solid and gaseous carbon dioxide, the dry ice and the CO2 that's in the container to come to equilibrium. And now you can see the pressure's gone down from the 15 pounds per square inch we started at to a little more than 10 right now. So I'm just going to take the thermocouple gauge and just check the temperature down inside there. We'll see what we get. It should be the temperature of dry ice at equilibrium with its vapor. But it could be a little warmer given the circumstances here, but I'll just stick this down in there and we'll see what we measure after things have a chance to settle out. See if I can set that up there and just move this around a little bit and see what we got. The cylinder or the sphere should have about that temperature. Obviously, the effect is relatively small. I mean, we started at 15, we dropped about 5 pounds per square inch. So a small difference in temperature is not going to make a lot of difference in the reading, but it will illustrate the principle. So we're right at about 76 Celsius below zero, minus 76 Celsius. And it seems to be coming down just a bit. So you might call it minus 77 Celsius by the time it really equilibrated. And that's the temperature, presumably, of the sphere, which is embedded down in there. And I've tried to have the thermocouple in contact with it. You can see I brought it back out now, and the temperature is rising up again. Let's put the top back on here. And so what we've demonstrated is that by lowering the temperature of gas in an enclosed volume, we reduce the pressure. And we started out with atmospheric pressure at the earlier, essentially room temperature. Now we're at the temperature of dry ice, and the pressure's dropped roughly 5 pounds per square inch, but you can actually read that gauge maybe a little more accurately than that to compare that to what we would expect. Now I've removed the sphere from the cooler and just letting it sit here in the room, and we'll watch the gauge come back up and come back and show you what happens after several minutes after everything's had a chance to warm up. Well, we're back again to measure the effect of changing the temperature on a closed volume of gas. And this time I've got a tub of boiling water. So there's back here in the background, there's a metal canister that it is sitting on a hot plate. It's been sitting here heating up for a couple of hours, And this is the metal sphere which we've used in other experiments in this series. 10 centimeter diameter metal sphere connected to a pressure gauge. Currently measuring atmospheric pressure because it was disconnected and reconnected at room temperature. And I have a thermocouple which can be used to measure temperature. So just hold it up here and put it on that. You see it's measuring right now about 19, going on 20, 21, roughly 21 Celsius, 20.8 it says here. And then the boiling water behind us, just to show you that it really is boiling, a little steam coming off of it, measures 99.0 Celsius. So we know that when we put that sphere in there, it's going to come to equilibrium at something like that temperature. And I'll just do that without making too big a mess. So I'm just going to pick this up. I'll drop it in the water. It will not go all the way in, though, because it's wants to float, and it's a little warm to hold. So I'm going to have to. What I'll have to do here is grab it as best I can with a pair of tongs, try to hold it, and then depress it a little bit here, and you can see pressure's going to go up. Problem is I don't want that plastic to get down in the boiling water too much. I don't know whether it'll handle that. See if I can push it down a little better. It's pretty well immersed in the boiling water right now. So you can see that gauge a little bit. I'm just going to let it sit here for a second. I'm going to go over and zoom in a bit. Let you get a better look. Gauge. And then I'll go back. While you're looking at that, I'm just going to take hold of the ball and try to get it a little better submersed, but I think it's pretty much all the way in right now. So the temperature of that sphere should be close to the temperature of boiling water. Will have dropped off a little bit, of course, because the sphere was colder than the water when I put it in there, and it's taking a while for the water to come back up to its equilibrium. Since the water is boiling, it will stay at 100 degrees Celsius until it's all vaporized. So that temperature is pretty stable. So now that way you can see the effect of heating up a sphere. And I'll put it back over here on the styrofoam and let it cool off a bit. So now you can see after the ball has had a chance to come back to room temperature, the pressure has dropped back again to atmospheric pressure. So we've used this system to demonstrate that you can cool a gas volume, or you can heat it, and that the pressure follows that, as we'd expect from the ideal gas law. So we made two fundamental measurements with this simple device. We looked at how the volume affects the pressure. Same amount of gas in this volume, but we decreased the volume, so we increased the density of molecules per unit volume, and that led to a pressure increase. And then we took this chamber, which is still a little warm from the experiment that we just did. We heated up a fixed volume of gas, and that also increased the pressure. But now the density is the same. We have the same number of molecules per cubic centimeter in this 10 centimeter sphere, but the temperature is increased. So the idea here is that the temperature measures the energy that is in those gas molecules. And we have increased the energy density by putting energy into the sphere with the hot air gun. We increased the energy density too by decreasing the volume so that the same number of molecules were crowded into a smaller volume, increased the energy density. The pressure is really a measure of energy density in the gas.